Good morning, students. My name is Uzochukwu Bartolome Wobane. I'm going to be taking your physics this morning, SS1 physics. The topic before us this morning is elastic properties of solid. Elastic properties of solid. Specific objectives. At the end of this lesson, you should be able to 1. Define elasticity. 2. Identify elastic material. 3. State Hooke's law. 4. Solve simple problems using Hooke's law. Elastic properties of solids. Topic: elastic properties of solid. An elastic material is a material that regains its shape and size after undergoing a stretch or a compression. Any material that when you stretch it or you compress it and when you release it is able to regain its original shape. It can be the length, it can be the size, original shape and the size. Such a material is said to be elastic material. And the ability of the substance or the material to regain its original shape and size after it has been stretched or compressed is known as elasticity. I said elasticity is the ability of the substance or the material to regain its original size or shape after it has been stretched or compressed. Examples of elastic materials are rubber band, the rubber band you play with, the coil spring, those coil springs. You can see them in those old types of chair. The springs, you can compress them or you can stretch them. All those are examples, and there are so many examples of elastic materials. Now let's go to Hooke's law. Now, Hooke's law did an experiment. On elastic material, and he came to the conclusion to what we know as Hooke's law. When force is applied to an elastic material and release, it returns to its original size and shape. But if the stretching continues, a point is reached where the material can no longer regain its original size or shape. At this point, it has passed its elastic limit. Therefore, Hooke's law can be stated as: Hooke's law states that provided the elastic limit is not exceeded, the extension in an elastic material is proportional to the load or the applied force. Take note, provided the elastic limit is not exceeded, it is not passed. They didn't go beyond the elastic limit. The extension in the elastic material is always proportional to the force you are applying. But when you pass the elastic limit, Hooke's law is no longer obeyed. Therefore, Hooke's law can be expressed as mathematically as force proportional to extension. Force proportional to extension. Force proportional to E. That's F proportional to E. Therefore, in mathematics or in physics, when you remove the proportionality sign, you introduce a constant. Therefore, F is equals to KE. Now, where K is the constant of the spring or the wire, known as elastic constant or stiffness, it is a part of every material. Every material has its own unique force constants. Therefore, making K or the stiffness the subject of formula, we have the F. K is equals to F over E, where F is the force in Newton and E is the extension in meters. Therefore, the unit of K is Newton per meter. The unit of stiffness is Newton per meter. Graph of load against extension. If you get an elastic material and you apply force on it, when you vary the force you are applying on the elastic material, if you increase it occasionally, and you make a table of the force and also the extension, Now you will not discover when you use the data you have for the force, which is the load, and the data you have for the extension, to plot a graph of load against extension, that is force against extension, you will discover that what you're seeing is the graph of load against extension. From O to P, Hooke's law is obeyed. That's why you see that from O to P is a straight line. At this point, Hooke's law is obeyed because it's still within the elastic limit. But E is the elastic limit. When you pass the elastic limit, Hooke's law is no longer obeyed. The extension is no longer proportional to the force you're applying. Therefore, at this point, you now discover that it has passed. When you pass the elastic limit, you get to the yield point. At this yield point, the material has lost its elasticity. Therefore, from O to E is the elastic region where Hooke's law is obeyed. But from E to B is the plastic region. At this plastic region, the material no longer obeys Hooke's law, and even if you release it, it cannot return to its original size. Then you get to B. The B is the last point, which we call the breaking point. At this breaking point, the material is completely disformed. It starts breaking to cut, or it is deformed, and it can no longer return to its original size or shape. From there, you could discover that a plastic material is a material that when you stretch it, or when you extend it, or when you compress it, when you stretch it or when you compress it, it can no longer return to its original size or shape. Such a material is termed plastic. Now, let's solve some examples using Hooke's law. Number 1, example 1. A force of 0.8 Newton stretches an elastic spring by 2 centimeters. Find the elastic constant of the spring. I repeat, a force of 0.8 Newton stretches an elastic spring by 2 centimeters. Find the elastic constant of the spring. Now the force, what do we have in the equation? We have the force. The first thing you do, write out what you have. You have the force. The force is equals to 0.8 Newton. The extension E is equals to 2 centimeters. But the SI unit of length is not centimeter, but is meter. So therefore you have to convert it to meter. Converting centimeter to meter, it will be 2 divided by 100, which is equals to 0.02 meter. 0.02 meter. Therefore, using Hooke's law, F equals to KE, we have it that 0.8 is equals to K times 0.02. That's the stiffness times 0.02. Therefore, the stiffness is equals to 0.8, making stiffness the subject of formula. We have K equals to 0.8 divided by 0.02. Therefore, our stiffness, which is K, is equals to 40 Newton per meter. 40 Newton per meter. Example 2. A force of 2 Newton stretches an elastic material by 30 millimeter. A force of 2 Newton stretches an elastic material by 30 millimeter. What additional force will stretch the material 35 millimeter? Assume that the elastic limit is not exceeded. The elastic limit is not exceeded. Okay, now, the first force we had was 2 Newton, which produced an extension of 30 millimeter. Therefore, you have to convert the extension to meter because millimeter is not the SI unit of length. Converting millimeter to meter, you divide by 1000. Therefore, you have 30 divided by 1000, which is equals to 0.03 meter. 0.03 meter. In this case, you have to note that for you to be able to get the additional force, you have to look for the stiffness first. When you look for the stiffness first, then you can now look for the additional force. Now also, we discovered that when they added the additional force, it gave an extension of 35 millimeter. You have to convert 35 millimeter to meter. We now have it 35 divided by 1000, which is equal to 0.035 meter. Then F2, we don't know. We are looking for the F2. But now, before you can be able to look for the additional force, you must first of all look for your force constant or your stiffness. Therefore, using Hooke's law, F equals to K, we have it that the force is 2, which is 2 is equal to K times your extension, which is 0.03. Therefore, I have 2 is equals to 0.03 K. And K, making K the subject of formula, we have it that 2 divided by 0.03. And therefore, our force constant is equals to 66. When you divide 2 by 0.03, you have 66.67 Newton per meter. Hear me, I didn't say 66.67. I said 66.67 Newton per meter. Also, having gotten the stiffness, now we can now use the stiffness to look for the second force that caused an extension of 35 millimeter. Therefore, using the stiffness now, we now have it that the F2, which is the second force, is equal to, using Hooke's law 2, F2 is equals to K times E2. The E2 is the second extension. We have it that F2 is equals to 66.67 times 0.035. That's the second extension. Therefore, when you multiply both of them, you will have it that F2 is equals to 2.33 Newton. 2.33 Newton. Now, this is the second force that produced an extension of 33 millimeter. So, but what was the additional force that was added to the first force, which is the F1? Therefore, to get that additional force, we have it that additional force is equals to F2 minus F1. Therefore, we have it that F2, it would now be 2.33 Newton minus 2.00 Newton. And we have 0.33 Newton. 0.33 Newton is the additional force. Young modulus. Young modulus. If a wire of length, Young modulus, if a wire of length L in meters and cross-sectional area, that's A in meter square, is extended through an extension as E in meter by a force F in Newton. Now we have it that the stress or the tensile stress of that material is the ratio of the force to the area. Is the ratio of the force to the area. Therefore, tensile stress can be expressed mathematically as tensile stress or stress is equal to force over area. Force divided by area. Therefore, I have it F all over A, where F is the force and A is the area. The unit of tensile stress is Newton per meter squared. Remember, the unit of force is Newton and the unit of area is meter squared. Therefore, the unit of tensile stress is Newton per meter squared. Also, we have what we call tensile strain. Strain or tensile strain. The strain is defined, the tensile strain is defined as the ratio of the extension to the original length. The ratio of the extension to the original length. It can be expressed mathematically as tensile strain equals to extension all over original length. Extension equals to tensile strain equals to extension all over original length. Therefore, we have it at E all over L, where E is the extension, L is the original length. Tensile strain has no unit. It has no unit. Tensile strain has no unit. The unit of extension is meter and the unit of original length is meter. So meter cancel meter, therefore there is no unit. Now, therefore, we go back. Young modulus now. Young modulus can therefore be defined as the ratio of the stress to the strain. Young modulus can therefore be defined as the ratio of the stress to the strain. This can be expressed mathematically as Young modulus equals to stress over strain. Stress divided by strain. Energy or work done on springs an elastic string. Energy stored or work done on springs and elastic string. Since you are stretching the spring or the elastic material, and also you are compressing it, you will discover there is a displacement. Therefore, since there's a displacement and there's a force causing the displacement, therefore work is done. And if you remember when we did force in the topic work, energy, and power, you will discover that there we define work as we said that work is said to be done when a force moves a body in the direction of the force. When a force moves a body through a distance in the direction of the force. Therefore, following there, we said that work is done when the elastic material is stretched or compressed. Because when it's stretched or compressed, there's a displacement. If the force stretching a material makes an extension E, then the work done is given by work done equals to average force times extension. Work done is equals to average force times extension, which is equals to half F times E. That's the F is the force and the E is the extension. Therefore, work done is equal to half FE. Half FE. But from Hooke's law, it follows that force is equals to stiffness times extension. That's the product of the stiffness and the extension is force. Therefore, using KE to replace force in the first equation, we now have it that work done is equals to half, instead of F, we now have KE times E. Therefore, we now have it that work done is half KE squared. So the two formulas for work done is half KE, half FE or half KE squared. Note, the above formula for work done also serve as the formula for elastic potential energy. Please, the formula for work done in a spring is still the same as the formula for energy stored in a spring. So therefore, it's also the same as the elastic potential energy. Examples using formula for energy stored. Example 1. If a spring has a stiffness of 950 Newton per meter, what work will be done extending the spring by 60 millimeter? If a spring has a stiffness of 950 Newton per meter, what work will be done extending the spring by 60 millimeter? First of all, before you start calculating, write out what you have. We have it that our stiffness K is equal to 950 Newton per meter. Our extension is 60 millimeter. But millimeter is not the SI unit of length, therefore we have to convert to meter. Converting to meter, you divide by 1000. 60 divided by 1000 is equals to 0.06 meter. Therefore, now looking at it, we have the stiffness and we have the extension. Therefore, the formula suitable to calculate the work done here is half KE, not half FE. Half KE squared, not half FE, because we don't have F. Therefore, work done is equal to half times 950, 1 over 2 times 950 times 0.06 squared. That square is coming from E squared. Therefore, we have it that when you multiply all of them, you will have work done equals to 1.7 joules. Example 2. A spring is stretched 40 centimeter by a force of 15 Newton. What is the work done by the force? A spring is stretched 40 centimeter by a force of 15 Newton. What is the work done by the force? Write out what we have. We have the force. The force is 15 Newton. The extension is 40 centimeter. Therefore, you have to convert it to meter. When you convert, you divide by 100. And therefore, it's 0.4 meter. Now, looking at the question, we have the force and we have the extension. Therefore, the formula suitable to solve this question is half FE. Therefore, we have it that work done is equals to 1 over 2 times 15, that's the force, times 0.4 meter, which is the extension. Multiplying them, you're going to have work done equals to 3 joules. 3 joules. Now, you have been learning, but this is the time to prove whether you have really got something from the class today. I would like you to answer the following questions. Number one, I would like you to define the following. Elasticity. What is the term elasticity? 2. Define Young modulus. Define Young modulus. I also showed the formula. Number C. Yield point. I would like you to just explain yield point. Number 3. I would like you to state Hooke's law. Remember, state Hooke's law. You don't define laws, you state laws. Now, number 3. A spring of force constant 1500 Newton per meter is acted upon by a force of 75 Newton. Calculate the potential energy stored in the spring. Remember what I told you. The potential energy is still the same as the energy stored, and it's also the same as the work done. Number 4. A spring of natural length 1.5 meter is extended 0.0050 meter by a force of 0.8 Newton. What will be its length when the applied force is 3.2 Newton? I repeat. A spring of natural length 1.5 meter is extended 0.005 meter by a force of 0.8 Newton. What will be its length when the applied force is 3.2 meter? If you look at that question, you discover that we have the extension to be when a force of 0.8 Newton was applied, the extension is 0.0050 meter. So in order for you to get the length when another force of 3.2 Newton is applied, you have to look for your stiffness first. Get your stiffness. When you get your stiffness, you now use the stiffness to look for the extension. Now when you look for the extension, add it to the natural length, then you get the length when a force of 3.2 Newton is applied. Now, summary. To remind you of what we have done today, I would like to remind you that elasticity is the ability of the substance or the elastic material to regain its original size and shape after a stretch or a compression. And such materials are able to regain the original length and shape are called elastic material, and the ability is elasticity. Hooke's law. Hooke's law states that provided the elastic limit is not exceeded, the extension in elastic material is directly proportional to the load or the applied force. Therefore, it can be expressed mathematically as F equals to KE. F is the force, K is the stiffness, and E is the extension. Then the stress or tensile stress of a material is the ratio of the force to the area. Is the ratio of the force to the area. Tensile strain. Tensile strain is defined as the ratio of the extension to the original length. The ratio of the extension to the original length. Young modulus. Young modulus is the ratio of the stress to the strain. Is the ratio of the stress to the strain. Therefore, Y is equals to F over A divided by E over L. Remember, Young modulus, the unit of Young modulus is Newton per meter squared, and strain does not have units. We have come to the end of today's lesson. Thank you.